Well, in this example, we're going to use the universal law of gravitation to calculate a force between two objects in a really straightforward way, except this time those two objects are going to be a proton and an electron in a hydrogen atom. So we'll start by writing the universal law of gravitation, and we can just plug in all the values here. 6.674 times 10 to the minus 11th meter cubed per kilogram second squared is the universal gravitational constant. Not something you have to memorize, you can always look that up. And then the mass of a proton is 1.672 times 10 to the minus 27th kilograms, very lightweight particle. And the mass of an electron is even smaller, 9.1 times 10 to the minus 31 kilograms. So we're not going to expect this gravitational force to be very large. However, the radius is really, really small. The distance on average between a proton and the electron in a hydrogen atom is 5.29 times 10 to the minus 11th meters, and that gets squared. So we'll do our normal cancellation of our units, and we should end up with kilogram meters per second squared, which is a unit of force. That's the Newton. Now in this example, I'm going to just go over the use of a calculator. This is a TI-84 calculator, and I just want you to pay attention to how I use the exponential button in order to put in powers of 10. There's no reason to type in times 10 to the power of something. You can just use a button on your calculator generally labeled EE or EXP. And E on the calculator, or EE, means times 10 to the whatever. So our final number then, after doing that arithmetic on the calculator, is 3.63 times 10 to the negative 47th newtons. So you can see that that is an exceedingly small force. And in fact, it's not the gravitational force that holds atoms together. It doesn't even really play any significant role at all. It's really the electrostatic force, which is about 40 orders of magnitude, or 40 zeros, stronger than the gravitational force.